So just we will finish the last session in chapter 4. Company. So let me just, the first thing we want to take here, multiplication counting rules, which is, it's so if we have like some sequence of events and each event occurs in maybe, I don't know, n times. So imagine that, let's take this example, it will make it easier. So imagine we have like maybe a phone passcode, which is 4 digits. So imagine that you have like a phone and then you have like some of password and you want to find that password. So in each one, you can take the numbers from 0 to 9, right? So here, so the first digit here, we can take any number from 0 to 9, right? So how many number? So how many way you can write the first number? 0, 1, 2, 3, which is 10 times. So I have here, how many choice we have? 10. And then for the second one, will be the same, right? So it will be again from 0 to 9, which is 10. And here we have 10, and here we have 10, okay? So now if I ask you how many passcode you can create from 4, including 4 digits, it will be how many? How many?
I was going to say 10,000 because 10 times 10 times 10.
Yes, it will be 10,000, right? So you can have how many? 10,000 passcode you can create using 4 digits, right? So starting with number 0000 and then 00001 till you get 9999, right? Which is basically, it will be 10 times 10 times 10 times 10, which is 10,000. Okay, so this is the idea. So if you have a sequence of numbers, and each number you can write it in some ways. So okay, let me ask you this now. What about if we cannot repeat the same number? So here 0000 is one number, right? But what about if we cannot repeat those numbers? So the first digit will be any number from 0 to 9, which is how many? 10. Okay, so let me write it 10 here. Imagine that the first number I did choose number 7. So I cannot use 7 anymore, right? So the next 3 digits will not include number 7. So the second digit now, in how many ways I can write it? Still 9 or yes, 9, right? Because the first one was 10, and then the second one will be 9. Since imagine that I did choose 3, for example. The next one it will be 8, and then the next one will be 7. Okay. So now, if we have, if its numbers can be occur twice or 3 times, that's okay. So this is the idea in how many ways. So this way it will be what? It will be 10 times 9 times 8 times 7. And you can get those number, which is how many. Okay, great. So this is the example. I believe this is example, which is how many? Yes, it's 4 digits, which is, we did say the number of ways equal 1, 2, 3, 4, 10,000. So we can create 10,000 different best code. Okay, then the question here, what's the probability of guessing the correct best code on the first try? So imagine that, okay, I give you my phone. It's my phone now has a four digits code, best code. If I give you my phone, what's the probability that you will guess it from the first try? What's that? Yes. So basically, there is only one correct best code, right? So what we did say yesterday, the probability, we say that number of times A occurs divided by the total number. We repeat this procedure, okay? The total number. Yes, then the total number clearly is 10,000, right? And then how many correct best code is just one? So yes, the answer will be 1 divided by 10,000. So this is the right answer, okay, which is here. So we have 10,000 different way to create best codes, and then we have, this is 1 divided by like this, 1 divided by 10,000, which is this is the answer.
But each square represents 10.
Was that?
Each square represents 10. Like 10 different.
Yes. So in each square, you can choose any number from 0 to 9, right? For the best code. And then we have 4 digits. So each one, 10 ways, 10 ways, 10 ways, 10 ways, right? Then it will be like 10,000. So now if I give you my phone, you need like maximum, you will need 10,000 try to get the right answer, right? If you are lucky, then you are the code, it's near to the beginning, right? Okay, and then factorial rule. So let's see factorial rule. This is this we call it factorial. This, okay, n factorial. Okay, so we have 2 things or 3 things before we start. Let's say 3 factorial equal to 3 times 2 times 1, which is equal to what? 6, right? 2 factorial equal 2 times 1 equal 2. 1 factorial, it's just 1. So this is equal to 1 factorial equal to 1. And very important thing to know that 0 factorial equal to what? 1. So this is very important. 0 factorial 1, 1 factorial 1, and then the rest just start from the same number, go all the way to 1. So then 9 factorial, it will be 9 times 8 times 7, 6, 5, 4, 3, 2, 1, right? So now in general, n factorial, it will be n times n minus 1 times n minus 2, all the way till you get 3 times 2 times 1. Okay? Clear, right? So just focus on this one. 0 factorial equal to 1, 1 factorial equal 1. And then this n factorial, by the way, let me explain it here. I did say 3 factorial equal to what? Or just let's take 4 factorial. 4 factorial equal to what? 4 times 3 times 2 times 1. But
12 times 2 being 24, 24 times 1 being.
yes, but also I can write this one as what? As 3 factorial, right? So then 4 factorial, I can write it if I need it as 4 times 3 factorial. Okay?
Because it would be 4 times 6, which would give you.
Yes. So in some cases, you will find that you'll see it later. For example, we have in the top here 3 factorial, and here we have maybe 5 factorial. So instead of write from 5 going all the way to 1, just we write 3 factorial divided by 5 times 4 times 3 factorial, and then this one will cancel this one. It will be 1 divided by 20, for example. So now just this is the factorial, the definition of factorial, just arrangement with its order matter. So starting from the same number going all the way to 1, and then we call it just n factorial.
So basically for factorials, we're looking at whatever the factorial is the sum of the multiplication of each individual number at subsequent number.
Yes. Yes. So till now, just we will use it later, but till now, just this is just the definition of factorial. So this is here, we mentioned that 0 factorial equal 1, and then we have just going from the n, so let's say n minus 1 factorial, okay? And then let's see the example here, okay? Which is close to the second example I gave you. So now we have like some of those 4 companies, okay? So we have 1, 2, 3, 4, 5 companies, okay? So how many different, so now someone statistics like a researcher must personally visit the president of those companies, 5 companies, right? So the first step, how many different travel ways he can visit? So now he wanna visit each company just one time, right? He wanna visit all those companies. So the first visit, so how many visits he will do?
One of each is going to be
5, right? So let's do it the same. This is the first visit, this is the second, the third, the fourth, and then 5th, okay? So now for the first visit, how many choice he has? So he can choose anyone from those 5 companies, right? So he can choose any one of those 5. So he has how many ways? 5, right? He can choose the Nelson, or I don't know, the Harris, or right? So for the first visit, he has 5 choices. Imagine that he did choose this one, say he will not visit it anymore, right? So then the second visit, how many choice he had? 4. Imagine that he did this one, and then 3, and then the next one he has those 2, right? Choice from those 2. Imagine that he choose this, then it will be 2, right? And then the last visit he has to go to this one, which is 1. So this is equal to what? 5 factorial, right? Okay, so then how many different ways? 6 times 4, 24, 24 times 5, it will be 1. 120. So he has like 120 different ways to visit those.
5 different possible combination of visiting each of those. When you said ways, I was imagining like getting there by plane, getting there by.
Oh no! Different ways to choose a number, to choose how many. Yes. So now like 5 places, and then depend on what, the first choice or the second or the third. Okay, so he has like 120 different ways to visit those companies. Okay, let's see the second one. what's the probability that the president are visited in order from youngest to oldest? So now the probability here in the bottom will be what? 120 for sure, right? It's all different ways. Why? Yes, you're right. Because we have just only one combination that the order of those presidents, they will be in order from youngest to oldest, right? It's only one combination. So this is, it will be 1 divided by 1.
So it gives
20.
1008.
Okay, so this is the first choice, the first one. The number of different travel. It will be 120 ways, and then the probability is, yes, 1 divided by 120, which is only one like right or correct combination that did the president from youngest to oldest.
So then it would be like, so when you divide it, you get 0 or 0.008. So it'd be like 0.008% chance of that occurring.
Yes. So usually for probability, yes, use like 3 digits. So it will be 0.008, right? Yes. So I mean, just only one. The probability that their age will be in order, yes, 0.008. Okay, and then how the ways now we have 2 different things, which is if we want to select. So imagine that we have how many students here? We have 5 students. And I want to select just 2 from those students. In how many different way I can select 2 students out of those 5? Got that question? So how many? So I have 5 students here, right? I want to select just 2. Those 2 or 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 those 2. How many different way I can select 2 students out of 5?
So 2 over 120 or 2 out of 120.
No. So we'll take it now. So, but before we start, it's really important if the orders matter or not. Is it different if you select you first and him second, or him first and you second? Is it different or no? It might be important. I mean, might be the order of selection is important. For example, if I want to select the first one to be president, and then the second one to be vice president, then the orders matter, right? But if I want to just put them in some committee, so then the order does not matter. So now to select 2 students out of 5, we have 2 ways. The first way, if the orders matter. The second way, if the order doesn't matter. President and vice president, then we have to select them in order, right? But for committee of 2, then no matter if select the first one, or I mean A and B, or B and A will be the same. So now, if the order is matter, we will use permutation, okay? So now if you have okay, if the orders matter, we will choose this one because this, so look to those 1 ABC, ACB, BCA, BCA, and all of them the three A, B, C, basically, right? But all of them in different order. In this case, each one of those will consider one choice if the orders matter. But if the order does not matter, all of them, I will consider them as one, right? Because it's okay to choose like, I don't know, A, B, C or A, C, B. All of those three, they will do the same work. So it does not matter the order for me. Okay, so the way, and then this is the combination. Then, so all of those, I will consider them as just one. Okay, so basically A, B, C and A, C, B is the same. So maybe if you can just to remember permutation and position. So the position is important, which is mean the order, or okay, and combination as a committee, which is just a committee of 2 or 3. So the order does not matter. So here, no order. Okay. So now let's start with this one. So you will use this formula. This is to select R out of N, to select R out of 10. So in our question, it will be selecting 2 out of 5. It will be N factorial, which is 5 factorial, right? Divided by 5 minus 2 factorial, right? So this one, you can see it's like this, and in some books, they do it like this. 2 out of 5. So that's in how many way we can select 2 out of 5. So 5 factorial, this is 5 factorial divided by 5 minus 2, it will be 3 factorial, right? So the top, it will be 5 times 4 times 3 factorial divided by 3 factorial. So this will cancel this, and then it will be 20. Right? Clear? Clear? So I see it's clear, and is it clear? Okay. So now,
is it possible to do this with the boxes again? Because the box that you use.
It will be not easy. Let's do it for.
Like you did the boxes for the 4 code.
Yeah. So let's do this then. It will be. I mean, for like this example, it will be too much, but. So let's. If we have 2 out of 4. It will be n, which is 4 factorial, right? Divided by 4 minus 2, which is 2 factorial. Let's just applying this formula. It will be 4 minus 2. It will be 4 factorial, and we have here 2 factorial. Then 4 times 3 times 2 factorial divided by 2 factorial, and this is equal how many?
12.
It's 12. It's still too much, right? So let's see. So if we have like 2 out of 3. So if we want to do it, I'll explain more. This is if this is 3. So that will be what? Right. So it will be here 3 factorial, 3 minus 2. So it will be 3 times 2, and here we have just 1, so it will be 6, right? It will be 6 different ways. So imagine that we have A, B, C. So those 3, okay? So how many choice? We have A, B, C, this is 1. And then we have A, C, B, and then we have A, okay, that's you. And then for each one we have 2, and then we start. The second one will be BAC, BCA, and then CAB, and then CBA, right? How many now? Those six choices, right? And the same. So now, in how many ways we can select 2 out of 3? We have 6 different ways, which is 1, 2, 3, 4, 5, 6. And if you want to do it for 20, it will be, I mean, for the other one, it will be the same, but it will be what? It will be 12 different ways. So now, oh, sorry. So sorry. Now this is not right. Can you tell me why? Because now it's just those 3, not 2. I said select 2 out of 3. So I said select 2 out of 3, but all those 3, so we have to remove, right? Just we have to select 2 out of 3. So it will be like this. AB, AC, BAC, B, yes, like this, because it's selecting just 2 out of 3. You got the idea? I'm very sorry. Okay? So now we select 2. We select 2 out of 3. We have those 3. So, and we just will select 2. So 1, 2. And then 1 like this. 1, 2. And then start with C. 1, 2. Okay. And each time we'll select just only 2. And we did say, so now if the order does not matter, if the order, look to those 6 choices, if we don't care about the order, then this one and this one is basically the same, right? If the order does not, but then we cancel 1. And then, let's see, this one and this one is the same. Let's cancel 1. And then the third one, this one and this one is the same. Let's cancel this one. So if the order does not matter, the number will be equal just 3, right? So let's see it in the next one here. And then we'll go back to the other example. We'll go back to the same example, but just let's do the combination here. So the combination, it will be, the order does not matter. So choosing 2 out of 3 will be equal to what? 3 factorial divided by 3 minus 2, which is 1, times 2 factorial, right? It will be 3 factorial, and you have, 1 factorial, and here we have 2 factorial. So this is 3 times 2 divided by 2, right? Which is equal to 3. And we did say A, B, C, so it will be AB, AC, and then BC. Those 3 different ways, okay? So let's go back now to the example here they gave. Okay. So now let's look to this example here, selecting the horses that finish first second, and third. You must select them in the correct order. That's mean what? The order does matter, right? Okay, and we have how many horses? We have 19. Okay, so how many different, what's this word? Can you read it for me? Even the pencil does not work anymore. Trifecta. Okay. Even I don't know what those mean. But okay. So how many possible we have? So now we did say the order does matter, right? That's mean we will use this. How many? How many we select? It will be first and second and third place, which is 3. And then how many horses we have? 19. So 19 in the race, and then in how many different ways we can choose 3 of them, they will be the winner. First, second, and third, then the order does matter, which is here, it will be n factorial divided by n minus r factorial, right? Which is n equal to 19 factorial divided by 19 minus 3 factorial, which is equal to
5,814.
it will be 9. Yes. So to make it easy, let me maybe to make it easy for this one. So it will be 19 times 18 times 17, right? Okay, just to make it easy for you, look here. So we start from number 19 and then go 3 times. 19, 18, 17. That's 20. This is the answer. It will be here 19 times 18 times 17 times 16 factorial, and here we have 16 factorial, right? So this will cancel this. So basically, you start from 19 and go 3 numbers back, which is 19, 18, 17. This is equal to what? 5,000?
814.
So we have 5,814 possible, all right, to choose first, second, and third place for this race. Okay, so the number of ways, like 5814. Okay, so can you answer B for me? Is it the right, the number?
My calculator says it's right.
Yes. 5,840. Okay, so for B, what's the probability of winning by selecting this one? This horse will be the first, and this one the second, and this one will be the third place. First, second, and this one will be the third place. What's the probability now? Yes, you are right. So the probability will be only one combination. We will get those in order, right? Which is 1 divided by this number. Okay? So so we have only one combination, including first, California first, and then the second and third, right? So only one combination. So now here, how many horses we have? We have 19 horses, and we want to just choose 3 of them to be first, second, and third. Then the orders matter. Then we have to use permutation, right? And this is the number of ways. And then for the second one, as you did say, it will be 1/1 divided by 5,814.
So now, if the order did not matter at all, it would be NPR.
So it will be if the order, so let's say that how many different ways we can select the first 3 winners. We don't care which one, the first and the second. So it will be like this: 3 out of 19 combination equal to n factorial divided by n minus r factorial times r factorial, which is equal 19 factorial. And here it will be 16 and 3 factorial. Okay. So it will be 19 times 8, times 18 times 17 divided by 6. So you will be this number, you already have 5,814 divided by 6. Okay. So now what about if we have some items is identical? So imagine that I have to choose, let's say, and I want to just give an example. So imagine that I have like 5 books. Okay. Or let's say I have 7 books. But out of those 7 books, I have 2 exactly the same books, statistic, for example, stat books. 2 stat identical books is exactly the same. So in this case, just if I want to choose the number of ways I can choose those books, it will be 7 factorial divided by, if I have like books exactly the same. In this case, so imagine that, okay, I have another 3 here now. So it will be equal to 7 factorial divided by 2 factorial, 3 factorial. Since those 2 exactly the same, it's no matter to choose the first or the second, right? So in this case, it will be 7 times 6 times 5. And you can find this number, which is the 7 times 5 times 4 times 3. If we have some items exactly the same. And you see some one more example here. And the selection will be without replacement. That's mean when you select one, that you will not put it back, right? So if imagine that, so I have to select one that I will not put it back, then I have to choose the second one, which is exactly identical of the first one. So let's say for this one, I have 10 questions. So for a particular survey, I have 10 questions. two of those questions just exactly the same. And other three, so we have two identical questions and I have three also identical. So how many different arrangements are possible for those questions? So how many questions I have? I have 10. It will be 10 factorial divided by the number of those, divided by those number identical, right? It will be 2 factorials times 3 factorial. It will be here 10 times 9 times, I don't know, all the way to 4, and then divided by 2. Right? So it will be this number. So 10 factorial divided by this number. So the number will be, those will be just without, so how many different way I create this surveys in different, I mean the arrangement for the order for those questions. Okay? So this number usually they said, okay, this number is really high, but the choice is somewhere around the 1,000. But this is the way we can create that survey. And then the next one, the combination rule, which is we did say here the order does not matter, so we don't care if I get A first or B first. And this is the example. So we have lottery game, and we have how many number here? We have 5 lottery games winning the, so select jackpot required you select 5 different numbers. So now we have to select 5 different numbers from 1 to 39. Okay. And 5 number must be drawn in the lottery. The winning numbers can be drawn in any order. So here, we don't care about the order, right? So the order does not matter, or the order in any order. So the order does not make a difference. How many different how many different lottery ticks are possible? So we have numbers from 1 to 39. So then we have to select how many number? 5 right here. It's 5 different numbers out of 39, because we didn't start from 0, so we did start from 1. Okay, if we did start from 0 to 39, yes, then it will be 40, but now it will be 39. So this one will be n factorial divided by n minus r factorial times r factorial, which is 39 factorial divided by 39 minus 5 factorial times, oh, sorry, 5 factorial, right? So it will be 39 factorial divided by here and then how many ways? How many different 5 numbers you can choose?
I know.
Yes, it will be a lot. This number, right? No, it can't.
Not if I'm doing 39 times, 38 times, 37.
No, you have factorial.
I can't figure out how to do the factorial on this.
Mine gave me a different number. Let's see.
No, you have a factorial in your calculator. Right away, you can find it. Even you have the combination right away. You can find the combination in your calculator. I didn't use calculators for a long time, but I'm pretty sure that yours it has combination. This one, let me see this.
That
This
one does
one-
have the
Yeah, it
factorial,
does,
this
but
one.
give
Even combination, it has a combination.
It does, but it's giving me a.
This one has.
This is how you can do everything with this calculator.
You don't have a class on how to use this calculator?
You have a book, exactly the same as your book, how to use the calculator. Find it, elementary statistic, for the same author, how to use this one.
Mine gives me a different number.
Really?
Yeah. Yeah.
Really?
You're not factorial.
I'm trying to see how to find the combination right away. Because I'm sure this has the combination right over here. This is the combination. So I believe if you choose for
Oh,
example,
I was putting the wrong way.
this is this one combination. So now we have 5. I think you press this one combination out of 39. Oops. Then the other 39.
Oh,
Right? Google, don't use this one. For sure, do you see this one? It's already like you can find it right away. Okay, and it's the same. The next button you can see the permutation also. Okay, and then the same way, like, what's the probability that you will win this lottery? Why? Because you only have 5 numbers that they will win, right? The lottery, right? So if you choose those correct 5 numbers, you will win. So you have all those choices, but out of all those combinations, we have only one combination that they have the correct. I mean, you will win the lottery, right? So this is, it will be 1 out of this number. So if you select 1 5-number combination, your probability of winning is just 1 divided by the whole number of selection. Okay, so this is the so you can have 5 minutes maybe, and then we'll start the next chapter, which is probability distribution. You got it?
Shoots and ladders.
oh, I know that have this one there. Exact.
Well, because here, like, because the way they do it is put in the number. So 2.
Oh, we're not doing PRB. This one is the same.
Okay, so let's start with this one now. So now I think the rest of today will be not hard. It will be somehow easy. Okay, random variable. So we did many, I believe in first week, we studied some variables, right? We did say this is variable, and we took like some continuous data and continuous, the four level of measurement, or that we have continuous, we have discrete, and we have nominal, and we had ordinal, right? We did do four level of measurement, continuous, discrete, and then we have ordinal, which is a data, we can put it in order, categorical data, but we can put it in order, and we have nominal, which is like a hair color or eye color or blood type, that data we cannot even put in order, okay? So to say numerical, to say random variable, we have to have numbers. So this is one condition, it must be numerical, okay? So when I say numerical, what I mean, it will be either discrete or continuous. So the data here will be discrete or continuous for sure. Okay, and then a probability distribution, which is how to study or how to see that the behavior of that random variable, how the data will change maybe over time or over different values of those, if this random variable. And then we have like three formats. We can study the probability distribution. The first one, table. We'll introduce it as a table. And then the second one, it will be formula. And the third one, it will be graph. So three different ways to introduce the probability distribution, table, formula, and graphs. So that this random variable, we did say it will be discrete when countable, right? Do you remember when we did talk the level of measurement? We said discrete, it will be countable, and continuous, it will be measurable. Anything we can measure, then the amount of water, then continuous. The number of bottles I drink every day, it's discrete, right? So that's how we know the variable or the random variable will be continuous or discrete. Just to make sure here, when I say random variable, that's mean what? Numerical, must be numerical. So if I give you a variable, still variable, that's okay, still variable. The hair color is still a variable, but it's not random. Why? Because it's not numerical, okay? The random variable must be numerical, discrete or continuous. Okay, now what is the requirement for numerical for probability distribution? This is important. Just here we have three requirements. One must be numerical, which is from the definition of random variable. Okay, so when we have x and probability of x, all those values here must be numbers, numericals. The second one, the summation of all probabilities must be equal to 1. So do you remember the example when we, for two coins, what all outcomes if we flip two coins? We have head, 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 tail, right? Tail, head, and tail, tail. So those all outcomes. So this is the sample space for this experiment, right? I don't know if you missed that or not. So this one, the sample space. So now if the event A is, I don't know, maybe getting ahead. So in this one, look to this one. How many head we have here? 2. How many head we have here? 1. How many here? And how many here? 0. Okay. So now the random variable x, which is represent the number of heads we can get if we flip 2 coins, is equal to what? What the different value of our variable x? 0, 1, 2, without repeating. 0, 1, 2. So now the random variable will take those numbers. So now, bless you. So now this is the first requirement. First requirement, our random variable must be numerical, which is right. So all those numbers. So this is the first requirement, which is okay. Then the second one, the summation of our probabilities must be equal to 1, which is the value we will take here. So let's see how many zeros we have in our outcome here. 1. 1 out of 4. So this will be 1/4, right? Which is how many, the probability of getting 0, the probability of getting 0 heads is the number of those divided by the total number of outcomes. It will be 1, which is 1 outcome, divided by the total number, which is 4. And then, okay, how many times we get 1? 1, 2. Out of 4, it will be 2/4, right? So the second one, it will be 2/4. And the third one, it will be 1/4, which is 2 heads. So now, if you take this total equal to the summation of those probabilities, 1 plus 2 plus 2, 4 divided by 4 equal to 1, right? So now the second requirement is valid too. The summation of all probabilities equal to 1. What about the third one? The third one, every single probability for each value of this random variable must be between 0 and 1. Those values here. Each single value of those must be between 0 and 1. No negative values, no values greater than 1, which is right. So now this distribution here, and we did introduce a distribution using a table, right? We did say we can introduce a probability distribution using table, formula, and graph. So the first one here. So now if you see this question here, can we consider this table as a frequency, as a probability distribution? Say, okay, let's check the requirement. The first requirement, this variable must take the only numbers, numeric. The first condition, this one must be numeric, which is, right, all those values numeric. The second requirement, the summation of those probabilities must be equal to 1. And then the third requirement, each single value of those must be between 0 and 1. If I have those 3 requirements, then we can say this is probability distribution. Okay? So this is the example, which is exactly the same example we did. Okay? So X, the number of heads. So this is the definition of our X. So the number of heads when 2 coins, when we have like 2 coins, and then those numbers, the summation of those equal to 1, each single value between 0 and 1, then this is a numeric. right? So the first one, numerical random variable, and then the summation of those probabilities equal to 1, and then each single value between 0 and 1. So we can say that this is a probability distribution. Okay? And then the second way to introduce the probability distribution using a graph. So now, those the numbers, right? That means x equals 0, 1, 2. And then the probability of x equal 0.25, 0.5, 0.5. Can you tell me this, what's this graph? We did this graph before. What's the name of this graph? Histogram, right? This is histogram. What is the requirement for the histogram? We have to have real limits, right? The boundaries. Yeah. Because yes, because they all touching each other, right? All those columns, they're touching each other, so we have to find the boundaries. How can we find the boundaries? Yes, so now just we have one value, so minus 0.5 it will be, and then plus 0.5, 1.5, and then here it will be minus 0.5. Sorry, this is just 0.5, right? 0 plus 0.5, right? And then 1 minus 0.5 equal 0.5. And then 1 plus 0.5 it will be 1.5. And then here it will be 1.5 to 2.5, which is here. You can see it clear. So this is negative 0.5. And this is 1.5 here. And this is this is 0.5. And this is 1.5, and this is 2.5. Okay, so now from negative 0, let me do it in red maybe, from negative 0 till 0.5, the probability equal 0.25, right? And then the second one from 0.5, which is here, till 1.5, the probability is equal what? 0.5. And then the third one is the same way. Okay, so now this is a probability distribution using what? Using formula, graph. And the difference between this one, the difference between this histogram and the histogram we did before is what? The histogram we did before here, what we have? Frequency. But now we have probability. That's why we call it probability histogram. So then it was here just frequency, and here we have probability. Okay? So now if you see this one, the probability, comparing this probability to the frequency table we did in chapter 2, I believe. What the difference between this one and the frequency and so what those values compared to the frequency distribution we did before. So do you remember how many distribution we did? So we did frequency, and then we did the relative frequency, and then we did percentage, right? And you remember the relative frequency, the summation of relative frequency equal to 1, right? Relative frequency basically is what? The frequency for each variable divided by the total of those variables, which is exactly what we did here. If you look to this one, here. So if you look to this one here, this is exactly what we did. So this is the frequency, how many is repeated. So just look here. 0, 1, 2. If I say the frequency here is what? How many zeros we have? 1. How many ones we have? 2. How many? 2 heads is 1, right? The total of those frequencies is 4. And then when we found the relative frequency is 1 divided by 4, 2 divided by 4, and then 1 divided by 4. And the total is 1. So now, instead of using this, we just, which is exactly the same. Okay? So relative frequency and probabilities will be exactly the same. Just when we have frequency table, x bar equal to what? Summation f times x divided by summation of f, right? So let me write it like this. Summation of x times f divided by summation of f. This value is what? Is the relative frequency. And later, when we take the relative, the end of this class, you'll see it. X bar or mu will be summation x times probability of x, which is this value, since we did this one is the same, right? So you will see it today, this one.
So why?
What's that?
Why?
Because instead of using the frequency, we'll use probabilities to find it. Yes, it's exactly the same way, but in different situations. Okay, so now we did introduce the probability distribution using formula, using table and using graph. And then the third one is the formula. Okay, so let's look to this formula here. They say this one is a formula for probability distribution. So we want to make sure with the 3 requirements, right? If it is a probability distribution or not. So now how many values of our random variable here we have? 3 values, 0, 1, and 2, right? So those are the values, 0, 1, and 2. Okay? So if just take 0 and plug it here, so it will be probability of 0 will equal 1 divided by 2, 2 minus 0 factorials times 0 factorial. This is equal to what? 1 divided by 2. 2 minus 0, 2 factorial. 2 factorial equal to 2, right? And this equal to 1. So now this is 1/4. Right? Which is exactly the same value we did find here. It's exact the same value here, right? This one. And then the second one, if we plug 1, it will be 1 divided in this formula. Plug 1 in the formula up there here, this formula. So it will be 1 divided by 2, and then 2 minus 1 is 1. And then we have 1 factorial equal to 1 divided by 2 times 1 times 1, which is equal 1/2, which is exactly the same value here, right? 1/2. And the third one, we plug 2, it will be 1 divided by 2, 2 minus 2 factorial times 2 factorial, right? It will be 1, 2, and then 2 minus 2, 0 factorial equal to 1 times 2, which is equal 1/4 which is exactly the same value we did find here, the third one, right? So now, yes, we can say this formula is a probability distribution. Why? Because the first requirement, all those values for the random variable 0, 1, 2 is a numerical or discrete, right? And then when we plug 2 inside the formula, we got those 3 values. The summation of those values equal to 1, and each single value of those between 0 and 1. So now look to this example. Can you tell me, is this example, is it probability distribution or not? This one here. Why? Is it random? Is it probability distribution or not? This one. Check the 3 requirements. You have 3 requirements, right? Check those. No. Why? So the summation, yes, this is 1. The summation is greater than 1. So this summation must be equal to 1, right? So this is not equal to 1. So this is not the probability distribution. This one, we have one more. So we have 3 requirements. Check those 3, all of them. Yes. So those is not numerical. So those values must be numbers. Right? So so now for this one, we have 2 reasons. The first one, the summation of those probabilities not equal to 1, and then the values that the random variable take is not numerical. Okay, so but the second requirement is okay, right? Because all these values between 0 and 1. The second requirement is okay, but the third requirement, okay. The first and the second is not valid here. Go back to those requirements here. So the first one here, you can see it is what? Numerical, not categorical data. Okay. Then the second one is the summation of those probabilities must be equal to 1. And then the third one, each single value must be between 0 and 1. Okay, so let's see this one now. Determine whether the value is discrete random variable, continuous random variable, or not a random variable. So can you check for me the first one? Is it discrete, continuous, or not a random variable? The first one? Okay, so this is a, okay, yes, but it's discrete or continuous? Continuous. Why? Yes, so we can measure it, right? The second one?
That's the time to evaluate it. How many minutes this is going to take, how many hours it's going to take. It's not specific time. So
yes, great. Yes, it's time, then it's continuous. The third one? So we have discrete, continuous, or not random variable. What do you think? So you have three choices: discrete, continuous, not random variable. How? The color. So now we have a color, right? So this is our variable, color. Can you represent the color using numbers? It's not a random variable. So I said it's a variable, but it's not random. So we can still a variable, but a random variable must be numbers, discrete or continuous. Variable, okay. Random variable must be including numbers, either discrete or continuous. And then the last one, discrete. It's clear because it's a number countable, right? Okay. Parameters of probability distributions. And we did say, so the first parameter we will study the mean. We did say before that when we use parameter, we use the Greek letters, right? So mu equal to x times p of x, which is what I did over there, the other side in the whiteboard over there, right? So we can find, so those the formulas for how to find mu and standard deviation. So mu, mean, variance, and standard deviation, okay? So use the same way I did use all the time, like this. So for this, so this formula and this formula basically is the same, but it's easier to use the second formula if we have a mu equal, for example, 1.783.
So for that, that's not the symbol for standard deviation.
So this is variance.
Right, but when you're looking for variance, wouldn't you use standard deviation?
The standard deviation is just the square root of this. So now if we take the square root, it will be cancelled this. So sigma will be standard deviation. Sigma square is a variance. What the difference between variance and standard deviation?
It's just a square. Well, what about that? So what's the difference between the sigma and then the SX for?
One for this, so sigma for population and S for sample. So all the time we said any Greek letter, that's mean parameter, and for population. Any English letter for sample, that's we call statistic. Yes, if we take the square root, it's the standard deviation, okay? And then the expected value. So the expected value is exactly the same as the mu. So we can call it expected of x or just e, maybe you'll find it. So expected of x equal to mu. So e or expected of x is the same. It will be summation of x times probability of x. So now let's see this example. So if we want to find the mu, mean for this one, the mu equal this, right? So now what we want to do is look to this one like this. Do we have probability of x there? Yes. Do we have x times probability of x? X times probability of x? No. So we have to find x times probability of x, and then the next step, what we'll do, we take the summation of those values. So x times probability of x. The first one, 0, right? The second one will be 0.5. 1 times 0.5 equal 1.5. And then the third one will be 2 times 0.5 equal to 2 times 0.25 equal 0.5, and the summation equal to 1. So this is the summation. Summation x bx equal to 1, which is mean. This is mu, mean. Mean.
So that's the population.
Yes, this is for the population. Yes.
Statistics or number would just be X bar.
Yes, but here we don't have statistics since we studied the probability distribution. Okay. So this is mean, and then for variance. For variance, we can either, let me write them down here. So we have x, and we have probability of x. So we have 0, 1, 2, 0.25, 0.5, 0.25. And we did say the summation here equal to 1. And then we find x times bx. And we got this is 1. But now let's see here what we have in this one. So let's use the first formula. So we start from here. So we have bx, right? So we start like this, exactly the same way. We have probability of x. And then we want the operation inside parentheses first. X minus mu. Do we have x minus mu? So we have to take x minus mu first, and then we square, and then times this one, and then we take the summation. Okay? So the first step is x minus mu. And mu equal to 1, right? We did find it here, mu equal to 1. So this is, it will be x minus 1, okay? Where x, this is x. So the first one will be 0 minus 1 equal to negative 1. And then the second one will be 1 minus 1, 0. And then the third one, 2 minus 1 equal 1. The summation equal to 0. This is all the time 0. So x minus mu all the time equal to 0. If you didn't get 0, that means you have some mistakes. Okay? And then we square this value, x minus mu square. 1, 0, 1. We don't need the summation, this one, okay? And then the next step, what? We multiply this value, x minus mu square times probability of x, which is equal to, so now what we want to do, this times this. So the first one, it will be 0.25, right? Because 0.25 times 1, 0.25. The second one will be 0. And the third one will be what? 0.25 times 1, which is 0.25. And then we have to take this summation, right? So the summation equal to 0.5. So now we will use this one. So let this take this formula. Yes, so it's ready, right? So this one, the summation of this one equal 0.5. So sigma, basically, sigma square equal 0.5. This is variance. Let's see the second formula here, if we get the same answers or not. So let's just do it here. So we have to find x squared. X squared equal to what? 3 values. So so x and then x squared. So 0, 1, 2, and then x squared is what? 4, right? Just square the values. And then what we have to find this, which is x squared times probability of x. X squared times probability of x. Right? So let maybe put the probability of x so it will be easier. So probability of x here, which is those values, right? 0.25, 0.5, 0.25, and then x squared probability of x will be, so now we multiply this times this. So the first one will be 0. The second one, 1 times 0.5 will be 0.5. And then 4 times 0.25 equal to 1. And then we want to take the summation, right? Summation of this is 1.5. So now let's take this formula. This one. So sigma squared equal to summation, which is this value, right? It will be 1.5 minus mu equal to what? 1. We did find it here, right? Mu equal to 1. So square. So 1.5 minus 1 square equal to 1.5 minus 1, which is 0.5. Okay? So now you see that if we use this formula or this formula, we will get the same answer basically, right? So you can choose which one you want to use, but it's easy to use the first formula if we have the whole number of mu. So if mu like equal to 5, 3, 4, 7, it's easy to use the first formula. But if we have some digits with the mu equal 1.73, for example, then it's easier to use the second formula. So if we want to find sigma is the standard deviation of and equal is the square root of variance, which is square root of 0.5. Okay? And this is the way how they answer the question. So this is the mu, which is equal to 1. We did find that. And this is variance equal to 0.5. And this is how to use the okay, so it's just repeated. So this is mean, and this is variance. And this is the standard deviation, okay? Which is the square root of variance. Okay. So now, when you did find a mu, and you have your standard deviation, okay? So any value greater than mu plus 2 sigma is significantly high. So basically, any values here, it will be significantly high. And any value smaller than a mu minus 2 sigma, it will be significantly low values, okay? Any values here. And then the values in between here, it will be not significant. So let's see here, this example. We found that when we tossing 2 coins, the mean number of heads, a mu equal to 1, which is the same example we did, a mu equal to 1. And we did find sigma equal to 0.7. Use those results and range rule of thumb to determine whether 2 heads is a significantly high number of heads or not. So let me write it down again here. So this is a mu equal to 1, okay? And then we have mu plus 2 sigma, which is 1 plus 2 times 0.7 equal to what? 1 plus 2 times 0.7. So 2 times 0.7, 1.4. 1.4 plus 1 is equal to 2.4. Okay? And here we have mu minus 2 sigma. It's equal 1 minus 2 times 0.7. It will be equal to what? Negative 0.4. So any number here will be significantly high. And any number here will be significantly low. And any number in this here will be not significant. Okay? So now they're asking about determine whether 2 heads is significantly high number. So 2 is where? It will be somewhere here, right? Right? So we can say that 2 is not significantly high number. Or 2 is not significant, okay? So here, so significantly high number of heads is 2.4 or and above. Since 2 is less than, so it will be 2 is not significantly high number of heads, which is clear here, right? 2 will be somewhere here. And we say that if we have 2.4 and above, it will be significantly high. So 2 is less than 2.4, then we cannot say that 2 is significantly high number of heads. Okay, and then we can say that X is significantly high number of success if we have probability of X or more success less than 0.05. Okay, so this 0.05, we did say this is the probability of getting results just by chance. So this number 0.05 might be reduced to 0.01 if this research related to human being life. Okay, and the same way we can say this X is significantly low number of success if the probability of X or less success or fewer success it will be 0.05. I think we have the we did say if they ask about the expected number, exactly is a mu. So mu equal the expected X. Okay, which is here. So now let's see this question. Okay. So for this one, A, does the table show probability distribution? Is it probability distribution here or not? The 3 requirements. I see number 1 and number 3 is clearly okay, right? Because we have numbers here, all those numerical, which is this is the first requirement. And the third requirement, each single value of those must be between 0 and 1, right? which is okay. And the third requirement is what? What's that? The summation is equal to 1, right? Is it or no? So if you add those numbers together, did you get 1? Yes. So the first, yes, it is probability distribution. Okay. And then how can we find the mean? Mu equal to what? Summation x times the probability of x, right? So then you find x time probability of x for each value. So for example, the first value, it will be 0 times 0.0. This will be 0, and this will be 2, 3, 2, 1. And then the next one will be what's that? And then the last one, 444. And then the summation for this will be equal this value, which is 1.633. And we did say use 3 digits for mean, right? Okay, now for standard deviation, which is sigma equal to square root of summation x minus mu square times the probability of x. Or you can use this formula. Summation x square probability of x minus mu square. In this example, it's easier to use the second formula because of this value. Okay, so what we have to do, we have to find x squared, and then you have to find x squared times probability of x. So x squared will be 0, 1, 4, 9, right? And then you will find what? You will find this time this, which is this value, right? So the first one will be 0, the second one will be 3 to 1, and then the third one will be 4 times 0.434. 1.736, and then the last one will be 9 times 0.148. 1 point, and then the summation. .3. So now if you do this one, you should get this number, which is 0.8. Okay. And those are the numbers here. How to calculate them. I think this is one of the book examples, maybe, or the assignment. Okay, let's take 5 minutes. Okay, and then we go to binomial distribution. So the most important thing you know about this, the last session, 3 things. 1, the random variable must be numerical. Really important. Random variable must be numerical. And then we have to know the 3 requirements for any probability distribution. The 3 requirement is what? The random variable must take a numbers, numerical. the summation must be equal to 1, and each single probability must be between 0 and 1. Okay? So this is really important. And then, so this is the any probability distribution. And then we will have two specific distribution, binomial and Poisson distribution. So those known. And we will know for each one when we can study this distribution, okay? So 5 minutes.
Oh.
Start your name. And put the date in the top, please. Today's date. Okay. So now what you see here, this is the summary for the last session, which is the last 50 minutes maybe. Okay. But now we will have one specific distribution, which are binomial distribution, and this distribution we have like four, I believe, four requirements for this distribution beside those. So this is general. We have to have 1, 2, 3 in any distribution. This 1, 2, 3. So any probability distribution, we must have those three. But if we want to say this distribution binomial, then we have other requirements. And if we want to say this distribution is a Poisson also, we have some requirement. So let's see what's the requirement for binomial distribution. So we have four requirements for binomial distribution. Can you just please pay attention for those things? So we have a lot of examples in this. Though the first example, we have a fixed number of experiment. We do repeat the experiment some. So the number of trials will be fixed. And usually we call number of trials represented as n. So n must be given a number, specific number, 2, 10, 5, 10,000, must be specific number. So if I flip this 10 times, how many times I'll get it right? Right? So I saw how many times I can get in 10, maybe 0, right? Or 1 max maybe for me. But I mean, if I repeat the experiment 10 times, how many times we will get the event that we are interested in? Okay. So I don't know. If I pick 2 of you, what's the probability that the one I'll pick will be male or female? Okay. So the first one, the number of tries must be given. 2, the tries must be independent from each other. So the first trial, it will not be affected. I mean, the second trial, for example, will not be affected by the first one. So in this, if we have this hat maybe, and we have like some marbles inside. So now what's the probability that I'll get if I select only one? What's the probability that I'll get red marble? How many reds we have? 2 divided by the total number, 5. So this is the first experiment. So now I want to do the second experiment. So if imagine that n equal 2 here. If I want to do the second experiment, then what's the probability that I will get red? This is depend on what? This is depend on the first trial. So if the first trial, I put the red marble back, then it will be okay, right? It will be exactly the same, 2 divided by 5. But imagine that the first trial, I did not return this red marble back. Yes, that's what I want. So it will be what here? The n here, in this case, it will be 4. Which is we start, I mean, so this is how many, so this is, let's say, n term, which is how many marbles? N equal to 4, right? And then the probability will be what? 1 divided by 4. 1 divided by 4. In this case, it's not independent. Why? Because the first experiment did some effect that in the second one, right? Because the total number decreased. So if we have example like this, we have to select with replacement. So we select 1 and return it first back, and then we select. Okay, so imagine that I want to select one of you. Select 1 and then back, and then randomly select someone else, maybe the same guy. Okay. So now, those trials, so we have no specific number of trials. Each trial will be independent from the next one, will not be affected by the first, or it will not affect the third experiment. So each single trial will be independent. And then the second, the third requirement, we must have just 2 outcomes from that experiment. Yes or no, agree or don't agree, male or female, head or tail. Just 2 outcomes. No, but we have red or not red. I don't care, but
Right, that's what I'm saying. You had the green in there, so the dots just before, if they were all red,
Oh.
then the outcome is only gonna be red.
yes,
So-
it doesn't. It's yes, it will not be binomial. Yes, but here imagine that I have some other different colors. No, I mean, so what's the probability I'm getting red? I don't care about the other colors. So red and not red for me.
Okay.
I see them, the outcome as red and not red. I don't care if it's green or,
So 2 out of 10.
right? Yes, it's 2 out of 10 here in this example, right? But I don't, the outcome must be to 2 categories. Red, not red. Male, female. Black, white, yes, no. So that I mean 2 outcomes. The one of them that I interested in, which is, for example, the probability of getting red. This is what I'm interested in. And the rest of colors, for me, I don't care. I see them all the same. Okay? So I see now red and not red in this case. Okay, and then the fourth requirement, which is the probability of success will be the same in each single try. By the way, so now X, the number of success, and then B is the probability of success. So B is the probability. So the value of B must be between 0 and 1, right? So we did say B is the probability, which is must be between 0 and 1. So now, if this value of probability must be is the same, treatment 1, experiment 1, 2, 3, and so on, okay? Which is here. So now, if you look here, the probability here is 2.5, divided by 5 in the first experiment. And then in the second experiment, it's 2 over 5, which is the same. So that's what I mean. But if without replacement, then it will be 1/4, right? Which is, in this case, probability of success is not equal. So the probability of success must be equal in each try. So B, probability of success in 1 try, but must be equal for all tries, must be the same. One more thing we mentioned, X and B, they studying both them the same concept. So X, the number of success, and B is the probability of success. So imagine that I am interested in getting head. Okay, so X, it will be number of heads. So imagine that I repeat the experiment 10 times. I have a coin and repeat it 10 times. So I have a specific number, which is 10 tries. And then the second requirement must be independent. So if I flip the first coin and I got maybe head, and then the second experiment, is it affected by the first one? No, right? So because if you flip coin, I don't know, it's just for the first one is 50-50, second one is 50-50. So the first experiment will not be affected from the first, so it's independent. And then we have 2 outcomes, which is head or tail, okay? And then the fourth one, probability of success will be the same. The probability of getting head each time will be 0.5, right? So this will be binomial distribution. So B, usually we call it's probability of success, and probability of failure, we call it Q. So B plus Q must be equal to 1. So B is probability of success, Q probability of failure, okay? And by the way, failure and success does not mean, success does not, probability of success that does not mean something good. So if I'm studying the number of students will fail this class, then the probability of success means failing, okay, the class. So probability of success, a probability that the event that I'm interested in will happen, no matter is something good or not, okay? Yes, so this example now. So now if we have selection, this selection must be with replacement. Rather than that, it will be not independent, right? So yes, now we can say this is independent because with replacement. Now what we have in this example, we have when adult is randomly selected with replacement, there is 0.85 probability. So this value is what? Probability of success, B, equal 0.85. Right? Probability that this person knows what Twitter is based on, okay. So now the first question, does this procedure result binomial distribution or not? So let's go back. The first requirement, we have a specific number of tries. So how many here do we have? Suppose that we want to find the probability that exactly 3 of 5. So now how many times we repeat this experiment? 5. So we can say n equal to 5, which is a specific number of tries. Okay. The second requirement, what? Independent trials. Is it in those trials, are they independent or not? Since we did say if the selection with replacement, then it is independent. So the second requirement is okay. The third one, we have 2 outcomes. So what outcomes we have? So I have a survey and we have a question they ask, and this question has how many answers? 2, right? So they said, yes, we know Twitter, or no, I don't. 2 answers. So yes, we have 2 outcomes. And then the last one, we have the constant probability of success, which is yes, we have. So each time here, each time we ask someone, there is probability 0.85 that he or she, they will say, yes, we know Twitter, okay? So now yes, so the first one, yes, this is probability distribution is binomial probability distribution. Okay. Now they asking you about N, X, B, and Q. So probability equal 0.85, clear, and N equal 5. So what about X? What's the value of X here? Yes, it's 3. So they ask you that exactly 3 out of 5. So 3 is X. And then we have Q. Q equal to what? Failure, the probability of failure, which is? No, you cannot say negative. It's a probability. So we did say probability must be between 0 and 1. So we did say probability here. Look here. I did write it somewhere here. See? B plus Q equal to 1.85. So it will be 1 minus 0.85. Yes. So Q will be 0.50. Okay. So now those requirements, one, we have 5 fixed requirement, or sorry, number of trials equal to 5. Independent, okay, because we have selection with replacement, right? And then for each those 5 trials, we have 2 outcomes, which is yes, I know Twitter, or no, I don't. And then the fourth one, the probability that when we ask someone that he know or she knows the Twitter, there is a probability 0.85, she will say yes. So yes, this is probability, this probability distribution is binomial. And then we have n equal to 5, x equal to 3, and then we have probability of success equal 0.85 and q equal 0.50. Okay. So this is this very important, this one, the 5% guideline for. So now we did say is the second requirement is what? Is independent. The trials must be independent. But if the sample size divided by the population size less than 0.05, let's say less than or equal 0.05, we can use binomial even if the trial not independent. Why? Do you remember the example we did that 3 adults, if we pick like 3 adults from United States, what's the probability that they are smoking? They are, I think we did that example. So because the sample size is, I mean, imagine that you have 3 out of 1,000. This will be for sure less than 0.05. That's mean basically when we choose for the first, let's imagine that the probability for the first experiment, for the first trial will be 3 divided by 1,000. And then the probability for a second, so imagine that we didn't return it back. So it will be 2 divided by 1,000, sorry. Right? Which is almost the same. So you see this value and this value almost the same. It will not be a big deal, right? If you divide by 100 or 99, for example. It's almost the same value. So the value, I mean, the end of the day, you will get almost the same probability if you did it with replacement or without replacement. So if you have small, very small sample size comparing to the population size, then you can use the binomial distribution. And this formula, so we did say we can introduce probability distribution using formula, right? How many ways we can introduce probability distribution? 3 ways: table, graph, formula. So this is the formula of binomial distribution. Can you look to this part? What do you think this part is? This one. What's this?
Oh,
the combination, right? Which is X out of N. So the probability distribution, you can write it like this. Probability of X equal to combination X out of N, probability of X 1 minus B, or just Q, N minus X. So now if you look to this one, B is what? Probability of success, right? And X is the number of success. So the number of success might be 0 up to 10. So if I flip coins 10 times, how many heads I can get? Maybe in 10 times, all tails, right? So 0. Or might be I'm lucky enough that, 10 times I flip them, I get all of them equal to head or tails, what I'm interested in. So this is probability of success, and this is number of success. What about skew? Probability of failure. And what about this one? N minus X. Trials minus the number of success, which is number of failure, right? So probability of success, number of success. Probability of failure, the number of failure. Okay, and this is just the combination. So here we have them. N is the number of trials, how many we did try this experiment. And we must say this is fixed, right? So might be this is equal to 10 or 15 or 1,000 or million. We don't care how big it is, but it's just this number is a fixed number. X, the number of success among N trials. And then B is probability of success in one trial or in any trial, and must be equal from trial to trial, right? So this probability must be equal from trial to trial. So for trial 1 and trial 5, 10, 15 must be equal, and the Q is the probability of failure. So let's take this example. So here they say exactly 3, which is probability of X equal to 3. This is what we are looking for. Okay. We did the same example we did. So we know N equal to 5, X equal to 3. What this is. Okay. And then this is probability of success, probability of failure. So the general formula, which will be, let's see, Bx equal to, here we have 5x, or let's write it right away. So it will be n factorial, which is 5 factorial. And then we have 5 minus x factorial. And here we have x factorial. B, which is 0.85 to the power x. And then we have Q, which is 115 to the power 5 minus x. And here x from 0 to n, which is 5. So this is our formula here. But now they're asking about x equal to 3. Okay? So just plug 3. So it will be here 3, 3, 3, 3, 3. Okay? So probability of x equal to 3 equal 5 factorial And here we have 5 minus 3 equal 2 factorial, which is 2. And 3 factorial equal to, or 3 factorial. And here we have 0.85. So this is the value we are looking for. So if you use your calculator, you can find this value. Okay? So this is one of the ways you can find this value. Look here. This is how to find it manually. Because when I use it now, we have different ways to find this value. But you should like understand how to find it manually first, and then I'll give you like the easy way how to find it. Okay, so now probability okay, what do we mean by this one? So if you ask 5 people, the probability that 3 of them, they will say, yes, we know Twitter equal 0.138. If we ask 5 people, the probability that 3 of them, they will say, yes, we know Twitter is this value, which is 0.138. The second, now using technology. Okay. So now, instead of this all work here, you will see how can we use technology, which is one of those. So this is your calculator. You can use your calculator to find this probability, or you can use just one of those, like this one, stat disk. Let's go to stat disk and see. Probability distribution, and then we go to what? Binomial distribution here. Okay. The sample size equal to how many trials we have? 5. And then the probability of success equal 0.85, right? And then what's the probability? They ask you probability of X equal to 3. So this is the value of the probability here, which is the same value we did find, right? So you can use technology to find this value probability. So again, analysis, probability distribution, binomial, and then you have the number of trials here equal to 5, and then probability of success 0.85, and then if so, how many the value of X, it's equal to 3. But if you don't put 3, they just give you every single value here. So this is a probability of X 0, 1, 2, 3 up to 5. Okay? Which is this one here. And you can use one of all of these. So Minitab, Excel, or this is online and free. So you can use this one all the time. Stat disk.
Is the stat disk going to be available during the exam also?
Yeah, you can use it. That's okay. I mean, just go to Google and find stat disk. It's statdisk.com. Yes, you can use it for your homework. So even for your homework, let me give you maybe something else. If you go to the data, and this is our book, right? Elementary Statistic 13, which is this one. And you'll find all the data is available here. Okay, so each single, so for example, this is the data for one of those examples. So you can even go to the data of the examples in the book, in your book, and you can practice in this one. So all these data is in our book. Okay. And then I think we have one more way to find it. Let's see it later. Okay, let's continue with this one. So this is the same, significantly high and significantly low. It will be the rule of 5%. So let's see here. So let's see this example. So here in this example, n will equal to what? How many times we repeat our experiment? For 60, right? So in binomial distribution, we have n and we have b and we have x. We need those three things so we can do binomial. So the number of trials here, 460. And then they gave us x equal to 252, right? And then for b, it's a coin toss, right? Which is what's outcomes we have? 2. Then since we have 2 outcomes, the probability of success will be equal to what? 2 outcomes. One of the outcomes we're interested in, and the other one we are not. It will be? Yes, it will be 0.5, right? So B equal to Q equal to 0.5. Okay, so now they're asking about, is it this value 252, is it significantly high number of success or no? So we did say we have the number of tries equal to 460, okay, and then we have to find the probability of x greater than or equal to 52, right? So is it easy to find this value or no? How?
I assume you subtract the 252 from 60 and it's way greater than.
No, I mean this one, when we said, so the first example we did probability of x equal exactly 3. This is easy. But this is not exactly 3. This is greater than or equal to 3. That means we have to find probability of x equal to 252 plus probability of x equal to 53 plus all the way to probability of x equal to 460, which is no way we can do it manually, right? Because if we want to do it manually, how many times we will repeat this process? Right, 209 times, right? So it's not easy to do it manually. Then we have to do this using technology. It's easy to do it using technology. Let's go back to this one here. So analysis, probability distribution, binomial. How many times we repeat this experiment? 460, right? The probability of success, 0.5. And then the value of x equal to what? 252. 252, evaluate. And then we want this probability, which is x or greater. So this is probability, this is probability of x greater than or equal to 52. That means we taking the summation from x equal to 252 or 252 all the way to x equal to 460, which is this one. Yes, so let's do it like this. So let's take this value. So here, so from 252, so x, so which is starting from here all the way to the end, which is almost the rest of the value is almost a zero, but so oops. So this the total summation. So but if we put it here 252, it will be easier. So now the probability getting exactly 252 is 0.0045, and then less than. So now this value is probability of x equal 252. Okay. And this value is probability of x less than or equal to 52. And this is probability of x greater than equal to 52. Okay, so then in some cases it's not easy to use the calculator, so we have to use technology to find those values. Okay. Which is, they said, at least 252. Just this value here. We did find it already, just 0.0244. And then the third way, using the table. You have table in your back, in the back of the book. So let's see. Yeah, you have it here. So let's see this example here. So we have B equal to 0.6. Okay, find the probability that exactly 3 out of 5. So we have n equal to 5 and x equal to 3, right? Find the probability that exactly 3 out of 5 adults believe in devils. Okay, so now so we did say that we need those 3 things, right? We need n, x, and probability of success. So just go to the table. So this is the value of B, which is probably equal to 0.6, and n equal to 5, and x equal to 3. So we have to take this and this, which is what this value. Okay, 0.346 using the table. So this is just screenshot from the table, binomial distribution table. So we need 3 things: B, which is probability of success, n, the number of trials, and x, which is the number of the number of what we interested in, how many success in n trials. Okay, so now what we are interested in, that the adults believe in devils, right? So the number of adults believe in devils is x. And again, we can use the technology for that, right? Which is just go here. We have 5 and probability of success 0.6. And we have this value exactly 3, which is this value. 3, 4, 6, right? This one, 0.346. What about the next one? What's the probability that the number of adults who believe in devil at least 2? So now here for B, still we have n equal to 5, and we have B equal to 0.6, but the probability X at least 2, which is mean greater than or equal to 2. So that's what we are looking for. So for this one, this is equal probability of X equal to 2 plus probability of X equal to 3 plus probability of X equal to 4 plus probability of X equal to 5. If you want to do it manually. Okay? Or just take the summation. So if you want to use this table, okay, sorry. If you want to use this table, then you would take the summation from 2 to 5. So we have, again, we have this, B is 0.6, and we have N equal to 5, which is those values, right? But they said B at least equal to 2. So you will take the summation of those values. 1, 2, 3, 4. If you take the summation of those 4 values, you will get the probability we are interested in. Or, since you know that summation of probability equal to 1, so you can say 1 minus those 3, which is using the complement rule, right? Complement rule, which is, we did say yesterday, we did say probability of A plus probability of A complement equal to 1. What do we mean by A complement? That what we are not interested in. Okay, we are interested in at least 2. So 1 minus, so let me write it here. So we have probability of X at least equal to 2. So we have probability of X equal 0, sorry, plus probability of X equal 1, and then plus probability of Sx greater than 2, this summation equal to 1, right? Because 0, so if you go to the table, and if you take the summation of all these numbers from here to here, this summation must be equal to 1. Okay? So now, since we are interested in this one, so we can take those two other sides. So we can say probability of X greater than or equal to 2 equal 1 minus summation, probability of X equal to 0 plus probability of X equal to 1. Also, we can write this one as probability of X less than or equal to 1. So probability of X greater than 2 equal 1 minus probability of X less than or equal to 1. Okay? But the easiest way to find this probability, just go to technology. Here, this one. So the number of trial we have 5. And then the probability of success equal 0.6. And then this value is equal to 2. This is the probability we are looking for. This is x is greater than or equal to 2. Easy, right?
And always have it so that at least 3 numbers after the decimal.
Yes, 3. So it will be here, it will be 0.913. Okay? So if we go back here, this is the number, right? 0.913. This one. Okay? So using technology, which will make things easier to find the probability. So now let's see the parameters of binomial distribution. So if I ask you to find the mean of binomial distribution, you don't need to do this, x times the probability of x, right? So we did say mu equal x times probability of x. It's easy. Mu equal n times b. N, the number of trials, b is the probability of success. And for variance, it will be n times b times q, n number of trials, b probability of success, q is probability of failure. Okay, and then if you take the square root of variance, you will get the standard deviation. Again, you can do this. It's easier to do it like this. So you have a mu here, mu plus 2 sigma, mu minus 2 sigma. Any number here significantly high. Any number here significantly low. And any number in this here is not significant. Okay? So here you have minimum, the minimum value here, the maximum value here, and then you have mu here, a mu plus 2 standard deviation, a mu minus 2 standard deviation. Any value greater than this, equal or greater than this, any numbers here will be significantly high. Any number here will be significantly low, which is equal to this value or smaller. Any number in between is not significant. I think we have an example for that. What's that? We have 1 more hour almost. Okay, so let's take them slowly. So mu, we did say mu equal to what here? They're asking for mean and standard deviation. Okay, so we have to have n, which is given for 60. And we have to have b, which is 0.5. Okay, so mu will equal n times b, which is equal to what? 460 times 0.5. Okay, so it will be 230 games. Okay, this is mu. And then the standard deviation. Standard deviation equal what? Square root of NBQ. And we already have NB equal to 230. It will be 230 times Q, which is 0.5. So this will be square root of 1 15, right? So this is A, which is those the values, okay? So the value of standard deviation equal 10.7. So now we got N equal 460, P equal 0.5, mu equal to 230, and sigma equal to 10.7 games. Okay. So let's see here. Okay, using the range rule of thumb to find the values separating the numbers of wins that are significantly low and high, right? This is the example we did. So here. Okay. So we have our mu equal to what? 230. And then here we have mu 230 plus 2 times 10.7, which is here. This value equal to what? 251.4. And then we have the same here to other side, minus 2 times 10.7.
208.6.
208.6, right? So now any number is greater than 251.4 is significantly high number of success. Okay, here. And then any number less than or equal to 208.6 will be significantly low number of success. Okay. So now they asking, is the result of 252 overtime wins in 460 games significantly high? So they asking about this one, 252. Just come here and check. 252 is where? Here, right? Somewhere here. 252. Then yes, 252 is significantly high number. Okay. Why? Because it's greater than 251.4. Yes, so those the values. So 208.6, right? We did find this value, right? Yes. Yes, so then 252 is greater than 251, then it's significantly high. Okay, again, so this one, we can say that X significantly high number of success if we have probability of X success or more less than or equal to 0.0%. So that's mean the probability that we will get number here or here, you will be less than or equal 0.05. And the same for this, the low, significantly low. So X is significantly low number of success if the probability of X or fewer success less than or equal 0.05. So Now, this is just the formula. So this is the formula here, which is the combination part, right? This part is the combination part, which is the number of outcomes that exactly accepts us in trials. And then, so let's take this formula, exactly this formula, and just put x equal to 0. So if we have one trial, that's mean x equal to 0 and 1, right? If we have one trial, so I'm interested in getting head. So one trial, if I get tail, then the number of heads equal to 0. If I get head, then the number of heads equal to 1. I mean, yes or no? So if you get the value of x 0 and 1, if you plug 0 and here in this part, it will be 1 factorial 0. Yes, it will be 1 minus 0 factorial, and we have here 0 factorial. So if you check this one, you'll find it equal to 1. And also, if you plug if you plug x equal to 1, it will be 1 factorial, 1 minus 1 factorial, and here we have 1 factorial, which is equal to 1. So if we repeat the experiment only one time, this part basically will distribute. And this probability distribution will be probability of x equal probability of success to the power the number of success qn minus x, and x equal to 0 and 1. This is another distribution. We call it Bernoulli distribution. And you will find that maybe Bernoulli experiment or Bernoulli distribution. If we repeat Bernoulli distribution in independent times, we will get binomial distribution. I believe one of your work assignment about that. So this is Bernoulli distribution. If we repeat Bernoulli distribution in independent times, we will get binomial distribution. Okay? Can you look to this example? Assume that different groups of couples use a particular method of gender selection, and each couple gives birth one baby. So we have, okay. This method is designed to increase the likelihood that each baby will be a girl, but assume that the method has no effect. So the probability of girl is 0.5. Assume that the groups consist of 56 couples. So now, before we start this example, is it binomial distribution or not? So let's check the 4 requirements for binomial distribution. The first one, we say 4 requirements we have. The first one, n is fixed. We repeat that experiment fixed n, the number of trials must be fixed. Okay, which is here equal to what? 56. So now we have n equal 56 fixed. And then the second requirement, independent. So can we say this experiment is independent? So how many times we will repeat this experiment? 56. So each single experiment should be independent for the other one. So let's say the first two couples having a boy or girl, they will affect the second couple? No, right? So then the experiment is independent too. The third one, we have only two outcomes. One we are interested in, and the other we don't. So how many outcomes here? Boy or girl, right? So the baby will be boy or girl, which is two outcomes. Then this is the third. The third one. The fourth one, B, the probability of success must be constant from trial to trial, which is here, they say, assume that the method has no effect. So the probability of a girl equal 0.5, which is constant. So now here we have B equal to 0.5.
You also have Q equals to 0.5.
Which is, yes, B equal Q equal 0.5. But we must know those two things. That Q we easily can find it. But if we don't have those two, we cannot use binomial distribution. And then if they will ask you about something. So now what's the value of mean and standard deviation? Easy. Mu. Since we know this is binomial distribution, then the mu n equal to what? N times B. That's it. Okay. Did you write your names? Oh, I have small. So we have one missing, right?
28 or something.
This one 28? Yes, so it will be 56 times 0.5, which is equal to 28. Okay? And then the standard deviation equal to what? Square root of NBQ, which is those values is 28 square root of 14. Okay? So this is the first 0.74. Yeah. Okay, so we did say mu equal to what? Mu equal to 28 and sigma equal to 0.74. Yes, 3 points. Okay, because it's 14.
Oh, you just didn't hear her 3. Yeah, she's saying 3.
Yeah. 3.74. Great. And then they said use the range rule of thumb to find the value separating. Okay, so this is what we find looking for, this one, right? So we have mu here, and we have mu plus 2 sigma, and we have mu minus 2 sigma. So mu equal 28, and here we have 28 plus 2 times 3.74, and here's the same. 28 minus 2, 3.74. The plus one, right? 35, this is 35.48.
Less than is 20.52.
Great. So now any value here, it will be significantly high. Any value here, it will be significantly low. So now let's check like 38 girl. 38 will be somewhere here, right? So yes, 38 is significantly high number. Okay, it's significantly high. Yes, 20.6, yes, and this is yes, okay. So this is the value of variance, it's the mean and standard deviation, and those. Okay, what's the time now? Okay, so we have Poisson distribution. So it can take a few minutes, and then at least we start with this one.
Are we adding an extra day class or no?
What's that?
Are we gonna do like online for a day?
Tomorrow we will do, yes.
Tomorrow.
What time tomorrow?
So tomorrow, or just I can record it. Yes, and then if you have like questions.